Hey, and welcome to our session on Next Level GraphML. If you ever wondered what GraphML is all about, or why I particularly am so excited about it, stay in the session. In short, we'll be talking about, first of all, what is GraphML all about and why does it matter to you? But then we'll also dive into some of the challenges you might be facing when you're trying to adopt it and generate value out of it. And that's then where I'm really excited to dive into some of the details of ArangoGraphML, our platform for GraphML, which was announced yesterday. And then to just kind of like get it real, we actually have a demo time and we'll see a live demo of ArangoGraphML. So stay tuned. First of all, if you haven't seen any of the other talks I gave, I'm Jörg, CTO here at ArangoDB, and I'm really excited that especially about this talk, I can bring in like all my past experiences and all my passions for that actually, from graph databases, large-scale distributed systems, cloud-native architectures, and then also my favorite topic, machine learning, all within one talk. So very happy to be here. GraphML, you might have seen that slide in my keynote yesterday, but I think it's the next level in GraphML. If we look at what big enterprises are doing, from Google, DeepMind, over Uber, LinkedIn, Spotify, and others, if we look at what's happening in research at the big neural network conferences like NeurIPS, for example, we see it's really picking up speed. And a lot of the talks, a large percentage, are actually using graph in one way or the other. And I think there's a quote here really nicely summarizes it. You can make better predictions, you can get better insights if you not only look at individual data points, but if you actually consider relationships and dependencies between those data points as well. And this, in short, is what GraphML is all about, but let's see that in a bit more detail. So, from machine learning to graph machine learning, this is probably the question I get asked most often is, hey, how does it compare to traditional machine learning? What is the difference? And I think this difference is actually that in traditional machine learning, kind of the core entity we use for training, we use for classification later on, is an individual record. It's like an individual row in a large matrix, for example. Or if we take this example here on the right, a social network would be one individual person. So in ML, imagine now we want to classify how likely someone is to churn from our favorite social network. And traditional machine learning, we would build a feature vector representing each individual user and then try to predict the churn from that. Just in reality, the world is connected. So here in a social network, we are also connected to other persons. And just imagine all your friends have left that social network as well. What does it do with your personal risk of leaving as well? Obviously, it will go up. First of all your friends have just left the network. The value of that network just decreased massively. On the other hand, most likely you will have similar reasons to leave that network as your friends had to leave it as well. And this is actually a property of real-world connected data sets, as that data is not independent of each other. So this is the assumption in traditional machine learning, is that all those records are being independent of each other. But here we actually see, hey, if all my friends have left, this is actually influencing my risk as well. And in kind of technical terms, we would call that homophily, that neighboring nodes actually share certain properties, share certain attributes. So in particular, they are not independent of each other. This is actually why so many companies and across so many different use cases are leveraging graph machine learning to get better insights. From logistics, where, for example, Google DeepMind is using graph machine learning for better prediction times on Google Maps. Supply chain management, where companies use it to classify the risk of, for example, individual packages, or also to identify like, hey, where are certain narrow points in my entire supply chain. Then recommendation and search from Uber Eats, who is leveraging graph neural networks for predicting which restaurant you should order from next, which dish you should order next, over to larger knowledge graph, where we actually use it for knowledge inference. Computational chemistry has been a long-time driver in the graph space in general, so not just graph machine learning, but also graph analytics. And it's very easy to spot once you start thinking about a molecule as a graph. It's atoms being connected by different bonds together. And so by leveraging graph technology, we can actually get much more insights from drug discovery, from trying to predict how certain proteins are folding. This is an open source project also mainly driven by Google, pretty exciting, to a lot of other applications in chemistry. Then financial services or also e-commerce in general, we can apply graph machine learning from insider trading detection, in general anomaly or fraud detection, towards credit scoring, to many other different use cases. Again, if you think about it, financial world, there's a lot of transactions where you have interactions between different people. So again, it's a connected data set. Okay. What is the core kind of like building blocks there? This is probably graph neural networks if we talk about graph machine learning. If you're familiar with like normal neural networks or in general machine learning models, it's a statistical model you train and then you can use it later on for inference. But graph neural networks, they're aware of the graph structure and actually take that into account. And you can also apply it to graph data. So for example, if you just think about a graph, you can leverage it for a node classification, putting like a label attribute on each of the nodes, which would be, for example, the case if we do churn prediction in our social network example earlier. You can also use it for edge prediction. Again, taking our neural network, our social network into account. That would mean we try to predict where edges are missing, so which person should be connected to which other persons. These predictions, they can actually not only be made on an edge or node level, you can also do it on an entire graph. And this is, for example, if we talk about molecules, where you want to estimate what are properties of certain molecules or how similar are they to each other. So just a question for like more complex graphs where the one graph is the same is a non-trivial question to answer. Those graph neural networks, they come in different architectures, and that's probably also beyond the scope of this talk to go into. But I think just certain dimensions to think about is like which kind of graphs they can understand or deal with. So the two big categories are probably like homogeneous graphs, if all my node types, my edge types are being the same. And then heterogeneous graphs, where I can have different node types. One node type might be a user, another node type might be, for example, a product. And so I actually can take that into account, and this graph neural network is going to be aware of it. The other property is kind of how easy does it apply to new unseen data? Do I basically have to retrain it or not? And so those are some of the properties you should consider before choosing one of the growing number of graph neural networks coming pretty much out at least once a week. So, sounds great. What are the challenges? Why is it so hard to adopt it? And so far only the large corporations are being able to build dedicated teams to benefit from it. I think it's also, which is the case in normal data science, it comes down to kind of like this outside view. So kind of the CEO view, how this entire data science life cycle is looking like. So basically, it's very simplified. Hey, you get some data, you build a really cool model, you train that model, you're done, you hand it over to the production team, and then they can benefit from it. Unfortunately, in reality, it is a bit harder. In particular, in graph machine learning, we already talked about the different models. I first have to choose the right model. This probably involves a large number of different experiments because I just have to try which model fits best. Experience can help, but typically I've still run a large number of experiments. Then also hyperparameters, how complex should my model be? And in the end, I end up with like a lot of code. So here, this is a notebook we also have online for you to check out about how to do movie recommendations. And that's about like over 2,000 lines of code. So you can see it's fairly complex and really requires expert knowledge to benefit from it. The other is that more general view for data scientists. So again, this actually holds true for traditional machine learning as well, where this writing of the ML code, so kind of like the CEO view here in the middle, like writing ML code, is really only a small chunction of the time and resources I'm going to invest in the overall process of building that. And by the way, that's also like why I've seen a lot of projects fail, because people believed it's only the small box here in the middle which I have to focus on. But really, everything around is so critical to productionize your model and actually get value out of it. So this is actually what like the data scientist or the different personas inside the machine learning cycle are seeing as their task. So this is why we're very happy to announce ArangoGraphML yesterday in Claudia's keynote. And this is our managed platform for making GraphML accessible. So really for people getting into the field, you can start with a low or even no code approach, just using the UI. Also the data preparation, the featureization, how do I actually like come from a categorical feature into something the system can use. So really no expert knowledge required. On the other hand, we still want to cater people who just want to solve that problem of like the overall ecosystem. So also experts who really know how to write their GraphSage model, they can benefit from the platform because we're just gonna upload their custom model and then basically apply it to different graphs. So take care of the entire ML ops topic for your personally trained model. It's very solution focused because in the end, we want to solve business problems. And to allow that focus, we included like all the ML ops from metrics, metadata, model management, as already mentioned, hyperparameter tuning and other things. It's enterprise ready, built on top of the kind of like long around ArangoDB, and therefore we can also benefit from the scalability and security which ArangoDB already provides. So how does kind of like the day in life of data scientists look like with that? Basically, we can take care of everything here on the right. So from feature extraction, even from the ML code, but I said that's kind of like the optional feature, so you can still drop in your own code. But the platform can really take care and basically allow you to focus on solving your business problems out there. So we are very happy to announce that beta, maybe some more details. The first beta is going to be focused on node classification as a service. You can start from various angles, so no code, low code we already mentioned. You can do that in the UI, in the wizard-like UI. You can still also access it through Jupyter Notebooks or an HTTP API. And so starting now, we actually have our beta trial period. So feel free to sign up. There's a link down here. Will also be on the last slide. And then participate in our beta trial. Why did we choose node classification? Because that's a question I've been getting quite a bit. It's a very universal tool. So we already saw we can use it for churn prediction in a social network. We can use it for supply chain management, for risk classification. We can use it for fraud detection or anomaly detection. There's another talk today about basically brand infringement detection. You can also basically just tag each individual product. How likely is it to be a genuine brand or how likely is it to be fraud? Traffic forecasting already talked about, like where potential slowdown points in your graph, and then for many other different tasks. So it's a very versatile tool, and it's also kind of easy to apply to an existing graph. So with that, how does the workflow look like for ArangoGraphML to achieve that, to do node classification? So you first choose an overall graph. Then you can kind of define your features of that graph. Again, this is something happening automatically for you. You train your model, and then kind of like the next step to actually benefit from it, you can apply your model to variously potentially also previously unseen graphs. It might be you're training on one graph and you apply it later to another. And then basically can access the results using any of the normal ArangoDB functionalities, such as AQL, such as other analytic tools, such as the data science library, etc., etc. So I always put it like that. You can imagine that being a user-defined function, which is just backed by a graph neural network, and therefore give you pretty exciting outcomes. How can you connect to the platform? We try to keep it as open as possible. So as mentioned, there are 3 different ways from a UI wizard, especially if you get started and don't know much about it. That's probably a really good way to get started. If you're a data scientist and you're already using Jupyter Notebooks, we basically have connectors for that as well. And if you just want to integrate it with a generic system, We offer HTTP APIs to access the platform as well. Talking about those Jupyter notebooks, I think one exciting thing is that we actually co-locate them with the platform. So we basically also have a hosted Jupyter notebook service for you to run your notebooks within the platform, fast data access, same enterprise-grade security, and also full GPU support so you can explore your data sets from within the platform. Okay, enough talking. Let's actually turn over to the demo. And so the demo, as you can probably guess by now, is about node classification. And you might have heard about the Netflix $1 Million Challenge, where it's about to predict like, hey, would it be a good movie or not? It actually came from the time when they were still sending out DVDs, but we in modern times, we actually take the viewing behavior, how many people and which people did watch a certain movie, and then question, can we predict a certain rating from that? So basically, is it an applicable movie for me to watch? All right, let's turn over to the demo and get started with that. As we're dealing with GraphML, the obvious first step in our demo is we're going to take a look at a graph. This is in ArangoDB, so we can pick any graph from ArangoDB. And just to maybe symbolize the data model we're seeing here, we're actually seeing movies and then their views. And basically what we can see here is we have two movies, then we have a number of people here in the middle who actually watched both movies. And based on this viewing behavior, we will try to predict the rating of the overall movie, which is data we have for like some of those nodes out here. All right, so first thing we do is we create a so-called experiment. Being a data scientist, we can handle multiple experiments. That might mean we're trying to explore different things. And so let's actually call that movie recommendation, movie rec, and let's create that one. And then we can go in. First thing, as mentioned, we are dealing with graphs. So let's select our graph here. It's going to be the IMDb movie graph. We can have several like expert settings. So for example, how do we want to split the data between test and train? But for the example of this demo, we'll just stick to the sample settings here, not select a custom strategy. Next thing for us to do, we need to kind of sub-select which data we want from our overall graph. This is especially useful as in many big use cases, you have huge graphs with a lot of different node types, of which not all of them might be relevant for your machine learning task. So here we're actually selecting the node and edge types which are relevant for us. So in our case, this is actually the entire graph. But we can also just easily have more things. So first selecting users here, then obviously the movies, and the last part we need is in between the views, kind of connecting both of them together. So from this, next we'll select which features we are interested in. We could easily select like all the features, but then our training task later would just take a bit longer. So just we'll select like the relevant attributes here. Those are the features and should recommend. And there we are good. Here we are good. We don't have to select anything on the views because views is really just giving us the structural information. But also in theory, we might have certain attributes on the edges here. So for example, timestamp or ratings if we wanted to go into more details. But in our case, we're really only considering this as structural information, who has watched which kind of movie. Last step before we can train the model is to select what is actually our classification task, like which attribute do we want to care about on those nodes. And so for that, we actually care about the label should recommend on the movie tab, on the movie collection, on the movie node type, because this is kind of like our goal out here. Great. With that, we can now kick off a training job. And we see what will happen in the background. The system will take care of all that, what we saw on the slide earlier, all the ML ops. So we'll train a number of different models with different hyperparameters, different model types out there. And then also we'll record all of that in the background for you so you can later on, if you want to dive into more details, go into that. And almost done here. Yes, so we are completed. And then comes the natural next step. We now have potentially, I think, 12 models in total here. And now we actually want to evaluate them and apply them to real data. So therefore, let's go to the next step here in our model. And again, we can select the database. We pre-select the database, which we've selected before, but in theory, it might be you have a totally different team working on like a database representing the training data. They might not even have access to the live data. So this kind of like this step might actually be done by a different team. Imagine you're in like a financial corporation or healthcare where some of the data scientists might not even have access to the full data. This is why in theory we could choose another model. And now we're just going to choose like the best performing model here. But you can see already in the performance numbers we saw just in the percentage back there, it actually really matters what kind of hyperparameters you're choosing. I think this is one of the big advantages of this platform, that we do a lot of that optimization for you in the background. As mentioned earlier, you could even at this step bring in your own model and then evaluate and apply it to the real data set. But for most people just starting out, basically choosing the best model here is going to be like a very good opinionated default. All right, so in this screen, we basically pull random examples, random nodes, and going to see like what is our prediction on that value. And so here, for example, Forget Paris has a pretty high rating. Stealing Beauty, Toy Story has a kind of okay rating. And we could go through more examples here. But for us, this actually looks like an okay prediction on the sample data. And therefore, we'll now just apply the predictions to the entire data set. And now it's being stored back in ArangoDB. So if you've like written your application against the database or against the platform, you can easily go back now and just use it through all your standard mechanisms, all the standard drivers, all the standard connectors out there, and keep using it. So in the end, I always like to refer to it like this is basically a fancy user-defined function, which is just happens to be backed by a model. And now you just applied that to your overall graph. What we actually use internally here is a PyTorch geometric adapter. You might have seen the other talk about PyTorch happening today, so I really recommend to stick around for that. But also if you use any other machine learning ecosystems, for example, Deep Graph Library, QGraph Adapter, or just Network X, we actually got you covered. So feel free to use our pretty extensive adapter suite to connect to that ecosystem. So that was Arango GraphML. So I think if I had to summarize it, GraphML really enables you to create unique insights and business value out of your connected data. And our cloud-first approach, so yeah, basically Arango GraphML, it's a fully managed GraphML solutions for all level of expertise. So that really allows you to focus on what you do best and accelerate your innovation. So sign up for our early access around here. Thanks very much for listening.